Okay, hello everybody. Real quick note. So fun stuff happening. I work for Google, and raise your hand if you've seen Android performance patterns videos. Not too bad, about half. Nice, nice, nice. Basically, my job at Google now is to tell all of you how horrible you're writing your applications, and basically try to shame you into stopping that. Really, that's it. I'm reviewing probably about 100 to 200 applications that come through the Play Store a day for performance evaluation and whatnot, and y'all got some problems. Yeah, so more on that a little bit later. Framework. Thanks, JJ. Everybody look at JJ. Shame, sir. Anyhow, like, what is this bald man doing? Hello, everybody. All right, so we are going to talk today about compression. Raise your hand if you've written a Huffman algorithm. Okay, arithmetic compressor. Hands up. Okay, BWT transform. Oh, a couple in the back. Nice, nice, nice. LZ77 compressor. 78. LZSS. LZW. LZFR. LZW. All right. That's a GIF man right there. GIF? GIF? I don't know. Okay. I'm serious. It's going to get better the more beer you have. All right. So today we're going to talk about compression with respect to networking. Why? Because it's probably one of the most important things that you're not doing right now. I mean, we like to spend a lot of time in the networking landscape talking about batching and prefetching and latency overloading and how to design for high latency environments and all this other crazy stuff, but we forget this fundamental property that your stuff is too big on the wire because y'all don't understand how compression works at its core. So let's get started on this. First off, you have to understand that assets that you're sending to your users are bloated. Again, I'm doing the analysis. I can see what you're doing, right? I know what's going on. And this is harmful for three reasons. The first one is not everybody's on 4G, right? There's a lot of people out there. The most of the world out there is on a 2G network, okay? And so the longer, of course, the slower the connection, the longer it takes to transfer the data, right? And that actually goes into the second part of this, which is that the longer it takes to transfer the data, the longer the cellular radio is active in your Android device, communicating to that network, thus draining battery. So think about that. That's a double whammy, right? So you get someone who's on a lower speed network, and you're basically screwing them over more, right? Because your assets are too big, right? And think about that. Like, the 4G guys get to run around with, high battery all day, and if it's 2G connection, get out. That's bad. Of course, this leads us to number 3, which is probably the most haunting part of this whole process, is that only in 4% of the world are unlimited data plans. So think about that for a second, right? The rest of the world is a pay per bit policy for their cellular networks, which means every bit your application is transferring to their device, they are paying for, right? Now, wouldn't it be amazing if one day they woke up and the Google Play Store told them how many bits they were paying for from your app? Don't make me do it. I will. Hopefully that's scaring a lot of you, right? I mean, all of you here, if you're not on a mobile, anyone from Europe, anyone on there you go, right? How you guys have had horrible roaming charges. There was a great web page that came out probably about 2 years ago that was showing the cost to load Microsoft.com was $4 for someone on a regular data plan in Europe, just to load a web page because of how large it was and the cost to load bits. Your applications force your users to pay for something when you transfer data. If it's not time, it's battery. If it's not battery, it's money, right? Bad compression makes your users unhappy. I'm going to tell them one day, fix it before then. Deal? Deal? Okay, yeah. Drink more. All right, so we're gonna fix that, right? So you all are not gonna have bloated assets anymore. You're gonna do the right thing. You're gonna be the smart thing. You're not gonna piss off your users. You're not gonna piss off the bald guy, the one bald guy in the room. Really weird. Statistically speaking, there should at least be 2 more in here. So I don't know if this is biased. Did they filter that down in the lobby? Okay. All right. So most of you are introduced to the concept of data compression in Computer Science 101 or Data Structures Class 102, where you generally see something called a Huffman tree, right? Invented by David Huffman back in the late 60s, who was actually a student of Shao and Fanon. And basically, the concept is, given some symbol, right, you can encode it with a number of variable bits in order to compress the data. And then that's it. That's all you're taught. Some of you may go on to master's degree programs or PhDs and whatnot, and you actually implement gzip, right? But that's really it. And there's a big problem with that, is because there's a huge gap between that theoretical concept of a compression data structure and actually what you're doing day to day in the trenches building Android applications. And the gap is so large and no one is covering it, right? I can give you this idea right now. No significant compression technology has come out since 1990. And that was when gzip became mainstream. Think about that. Like, if gzip were a human, it could drink now. Right? Probably have a couple DUIs, maybe did some stuff in college it's not proud about, right? Like, we've all been there. Like, think about that. Where else in computing technology has it been so stagnated for 20 years? And the reason is that there's just been a general loss of focus on these magical compression algorithms at all levels of computer science curriculum. And so let's talk a little bit more about that. Huge gap. Yeah, I should have clicked that earlier. So compression basics. So entropy. This is the term you need to know. This was defined by Claude Shannon, the father of information theory, back sometime after World War II, when he was allowed to actually publish all of the work he had done for information theory for the Allies during that time. Entropy as defined, it's a statistical theory that says the number of yes or no questions you need to ask to describe a piece of data in a set. Who's confused? Everybody, nope, nobody? Nobody was confused about that. I had to read that book like 6 times before I understood what the hell he was talking about. You all got it on the first time? So I'm that good of a teacher. False. You all are lying. Or there's more beer happening. Think of it this way. Binary search, right? Binary search, everyone's written a binary search. So let's say we've got a number line from 0 to 15, okay? And we want to look for the number 10. Okay, so of course we check the middle value and we say, is it higher or lower? Simple yes or no value, right? Is it higher or lower? Well, in this case, it's higher than the value we checked, right? So we get rid of the stuff that's on the lower end, and then we ask the middle value again. Is it higher or lower than this middle value, right? Simple yes or no question, it's lower. Is it higher or lower again, right? Higher. Is it higher or lower again? Lower, right? And of course, at this point, we've now found the number 10. Interesting enough, if you actually notice these bits that we've logged on the side, it's actually equal to the binary number of 10. Right? This isn't like weird magic voodoo. It's the basic construction of how information theory exists inside of our modern computing environment. Right? A binary search over a closed number range produces the binary value of that data. It's a simple yes or no equation defined by Shannon way back in the day. And since then, there's been really, again, no huge significant changes from this theory. You can think of it another way. Guess who? Who's played Guess Who? There's some 80s kids in here. That's good to know. I'm not the oldest person in here. Fantastic. Guess Who? If you haven't played it, it's a really weird game you play as kids, right? Basically, each of you are given like a row of people, and you pick one of them. And you take turns asking each other yes or no questions, like, does he have hair? Is it a male or a female? Right? Yes or no questions. And then, based upon the response, you get rid of some of your values, right? Now, the interesting thing is, if you look at the Guess Who game, my wife won't let me wear that t-shirt around anymore. If you look at the Guess Who game as a form of information theory, right? If each one of your yes-no questions exactly eliminated 50% of the options, you would be in a binary information system, right? Each yes-no question removes 50% of the question, of the potential results, right? So 50% had hair and 50% didn't, not like this room, right? That would be a binary system. Now, where things start to get interesting with the Guess Who game is when you get skewing, right? So let's say there's only one bald person in a room. Not that would ever happen. And you say, is the person bald? And the answer is yes. Well, you've just found the person with one bit. One question gave you one answer, and that was it. Of course, if you said no, well, now there's 29 other people that you have to then start asking questions about. When you start skewing data like this is where we get into the concept of variable length coding, statistical compression. The idea that the probability of an attribute on a piece of data is skewed based upon that data's existence. Lots of redundant mumbo jumbo. Again, theory. We'll get to the important stuff here in a second, right? So the problem is, this is all we've been taught. In fact, most of you probably haven't been taught how binary really works. Most of you are taught how to convert to binary, and how to convert from binary, and that's a great exercise for everybody. But as far as information theory is concerned, nothing. Who actually had an information theory class at university? 1, 2, 3, 4, 5? There's a lot of smart people in here. Only 5 of us have taken an information theory class? That's insane. It describes to you why no significant things have happened in compression in almost 20 years. We're a mobile environment. Pieces of data are flying around the world every second of every day, all around us, and we haven't done anything with compression in 20 years? Yeah. We're going to fix it. So let's talk about not the theory anymore. Let's talk about the application, right? So there's a long line of things between that theory and what you need day to day to make your app stop sucking and me stop being mad at you. Yay. The first one is archivers. We're going to talk about general data archival technology, right? So you have to understand this is the general lay of the land when it comes to compression. At the bottom of our rung is something we call statistical compressors. Right? These are things like Huffman, arithmetic compression, variable length codes. Basically, these take in a set of symbols, the probability of how frequent that symbol is, and assigns a variable length code word to it. So it bases itself on the statistical skewing of a data set. The more skewed it is, the better the compression you get, right? The less skewed it is, the worse compression you get. That's the whole point of this layer of data. That's all these transforms do. And quite frankly, like, the reason there's only 3 of them is because there's really nothing else you can do at that point, right? Like, you have this simple transform. Above that, we have something called contextual transforms. These are things like Limpel-Zev, LZ77, LZ78, LZW, LZSS, LZMA, LZHAM, right? A Burrows-Wheeler transform, move to front, delta encoding, run length encoding, right? Basically, this set of transforms doesn't compress anything. All it does is seek to transform the data so that it's more skewed for the statistical compressors. That's it. That's all it does. No compression is occurring at that point, right? So think about that. That's kind of interesting, right? We have this base level concept of information theory and how to produce compression, and then we've got a whole field of science that just says, how can we screw with our data more to make it more compressible, right? Above that, we have probably some of the most amazing research in compression technology since the 90s, but it's not actually anywhere close to being usable by average humans right now. Nowhere close. And like, it takes years to do a lot of this stuff, right? This is including like Markov, prediction by partial matching, context modeling, LPAC. What these basically do is they'll analyze your data, it'll run some statistics on it and say, I think that this would be best served by running LZ77 on it. Or, this looks like a BWT transform would work best. Basically, it's a meta level that analyzes your data to figure out what algorithms to apply to it to get the most compression out of it, right? This is considered cutting edge right now. If you go to encode.ru, which is like the place for compression nerds on the planet right now, it's run by some Russian dude who's crazy, about compression. Sorry, any Russians in here? Russia's cool. This is the stuff that's the cutting edge here. Of course, the problem is all of this, LPAC is really one of my favorite algorithms of all time because it actually has a neural net built in the compressor, right? So what it'll actually do is it'll actually analyze your data, feed it back into a neural net, and the next time it sees data that's similar, it'll go, oh, hey, I got some better results from that over there. So effectively, it's applying artificial intelligence to compress your data better. We probably got another 12 years until that's going to be able to run on anyone's device, because it roughly uses about 12 to 18 gigs of memory right now to get some good results. Now, above this, we breach into a different area that I'm not going to spend too much time on right now, and this is data removal. So if you're in a lossy compression set, so audio, video, images, things like that, you have to understand the human sensors, they're pretty dumb. Right? We have more capacity for information representation in our data on our computers than the human eye and ears can actually see. And a lot of times, we're very easy to trick. We're pretty much dumb primates, right? And so the lossy data removal stage actually gets rid of data that we just can't process or may not care about or may not notice. And of course, then that can be fed into the data modeling phase or the contextual transforms or the statistical compressors. This is how the modern industry of compression works, top to bottom. This is all you need to know, right? Anytime someone talks about an algorithm, it fits in one of those 4 buckets, period. That's it. Done. So let's talk about how this works in reality. gzip. Anyone know gzip? Yay. gzip is comprised of 2 stages. LZSS is a contextual transform, and Huffman encoding as a statistical transform. That's it. 20 years. We've been riding that guy. 20 years we've been riding that, right? And that's it. The backbone of HTTP technology is built on those 2 algorithms, and that's all, right? WinRAR. Any hackers in the house? Holler. Yeah, WinRAR. I'm surprised people were like, yeah, me. I love WinRAR. I torrent stuff. What about it? Want to fight? WinRAR is actually a variant of LZ called LZW mixed again with Huffman encoding, right? So it does a little bit different technology in the front, but then sends it to the same statistical encoder. BZIP2 actually does Burroughs Wheeler transform, throws that at a move to front algorithm, which is another contextual transform that actually works really well with BWT. So there's two transforms there before throwing it at Huffman. In fact, sorry, this is inaccurate. BZIP with no number actually uses Huffman. BZIP2 switched over to arithmetic compression once the patent expired on it a couple years ago. LZMA, 7-zip, anybody? 7-zip, some people. Yeah, some of you download movies, that's cool. I'm not judging. Yeah, all right, yeah, alpha bears, I'm not saying anything. LZMA actually uses a variant of LZ. There's actually like 3 or 4 variants that'll bounce between to what it needs. And that actually applies a Markov chain predictor. Any math majors in the room, Markov chains are fantastic data probability models. And so it'll actually create a Markov model for that and then throw that at an arithmetic compressor. And then ZPack is probably one of the most amazing compressors out there that's actually winning every single competition with compressing the human genome. ZPack, LPack are at the top of that, and those all use context modeling. And so basically it says, let's analyze this data, figure out which one of all of those sets work best, and then apply it, and then keep going and keep going and keep going. Like if you talk to anyone in the genetic sphere about human genomes and stuff like that, they all know that algorithm because it's the only way they can actually get their jobs done right now. Right? So this is it. This is the day-to-day stuff. This is the connection. So when you're using gzip or you're using LZMA or bzip, this is what's going on under the hood. So now let's talk about the practical stuff. There's 3 main things I'm going to talk to you about today that you're going to fix and be awesome. Yay? Notice more beer has happened since last time I asked that, right? Yeah, y'all getting it. It's cool. It's cool. So number 1 is images. Images are by far the easiest way to screw up the bits on the wire. These are the most bloated things you are sending to your users, and I know it because I can download it and look at it, and I can see it should not be that good looking, right? So first off, the first important thing is, let's talk about file formats for a minute. If you're an Android developer, there's a large bias for you to use PNG files. Stop it. Stop it. No more. No. 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 No more PNG files. They suck. And I'll get to that in a second. PNG files are really only useful if you absolutely need transparency, right? And let me ask you a question. If you're putting transparency in all your damn images, what are you doing, right? You don't need that transparency, right? Don't use PNG unless you need that, right? So reserve that for the assets that you absolutely have to have some transparency. I like how the people just left. Like, he said bullshit. Everybody out. The bald man said, screw PNG. All the desires, screw that guy. That's all right, I'm used to that. JPEG. JPEG fans, anyone? Okay, JPEG, if you don't need transparency, you should be at minimum using JPEG. Absolutely, there's no excuse here if you are sending images that don't have transparency to people and they're PNGs, I'm gonna find you and I'm gonna punch in your ear. And I'm gonna take a video of it and I'm gonna put it on Twitter, okay? The truth is, you should be using JPEG. Now WebP, round of applause if you know WebP. Some people, okay, WebP is fantastic because it actually represents the middle ground between PNG and JPEG. It allows you transparency, it allows you a lossless version of the data, but it also allows you lossy as well. And so with a single file format, you basically get the best of both worlds between JPEG and PNG, right? So here's the gist. If you don't need transparency, if you need transparency, use PNG and then feel bad about yourself as a human, right? Good. If you don't need it, then you need to evaluate whether or not JPEG or WebP is what you need, right? So at bare minimum, you're already using the wrong format. Fix it. Yay. Next. We're not done yet. Reduce quality, okay? There is a direct correlation between the quality of the image and the file size. I don't care what your designers say. They're wrong. They're wrong. Images don't need to look that good. None of you will lose like 90% of your business, right, by introducing 2% quality error in the images you send down. That's not how it works, right? Image quality is a scalar value for all these lossy compressors. Basically, when your artists export it, they get a little slider. They're like, 75, yay, right? I don't like how that looks. 100, better, ship it. No, no. 75 is great, it's perfect. You wanna know why? Humans are dumb, we're dumb primates. The way our cones and rods work, right, is we don't detect a lot of problems. And you can crank that quality level down really far before users will start to complain about it, right? Case in point, PNG, right? This is a 16 pixel by 16 pixel PNG file saved from Photoshop, right? At 24 bits per pixel. It's 2.74K. It's all red. There's nothing hidden there. 16 by 16, right? The reason for this is that PNG hides shit in its file format, right? It's a block-based file format where Photoshop can be like, hey, everybody, I like pizza, and then your phone is like, hey, everybody, you took this photo at the beach, wee, and all this crap is crammed in your PNG files, right? This is why when you actually go file, save for web, you actually get it down to 121 bytes. Raise your hand if you know for damn sure right now which one of these two your designers are using. That is why this is such a problem, right? No one thinks, no one looks at the back end of this stuff, okay? So let's talk about PNGs and why they're so crappy for a second. So how PNGs work, basically it's your pixel data and we apply the deflate algorithm, gzip to it, and you get lossless image compression. There is no quality degradation at all, which is why your designers love the fuck out of it because it looks amazing, right? They spend all that time making those images, it looks great, but you're paying for it. Your users are paying for it, right? How JPEG works is it applies one of those data removal pre-processing steps before passing it off to a lossless processor, and that's how you get that data, right? WebP works in a similar fashion. There's a lot of things that occur to remove data and remove things you don't care about before passing it off to compression. Now, but the good news is you can actually get lossy pre-processing to your PNG files. It's actually really simple. You just apply a lossy preprocessor and then hit save. Oh, that's it. There's nothing past that. That's it. Do that, right? So the idea is that you can actually go through and take your PNG file and actually apply a vector quantization algorithm or a color blocking algorithm or a truncation 565 pattern. Any of those things will actually work to reduce the dynamic range before actually saving it, and you're actually going to get a massive amount of better image compression as a result. And the good news is you don't have to write this stuff yourself. This is such a common problem. I'm going to blow your mind. This is going to be amazing. Everybody ready? Everybody ready? Get your beers. This is going to be great. This is such a common problem that over the past 15 years, over 143 separate applications have come up on the internet that just do this. How many of you knew they existed? That's like what? Maybe a fifth of the room? This has been such a problem for development of applications for the past 20 years that every single one of these people took it upon themselves to write their own version of the algorithm, right? So at bare minimum, if your designers absolutely want PNG files and they're absolutely locked into it, trick them, okay, and use one of these algorithms to apply a lossy preprocess. You can actually crank that quality level a lot further down than they're willing to give space on. And here's proof. Perfect proof, right? There's two images exported from Photoshop. This is a parrot from the Kodak image set, right? So I can use it publicly. Thanks, Kodak. On the one side there, 164K. The JPEG quality is set at 100, right? Fun fact, if you're just grabbing JPEG and you're actually like link compiling it into your server-side code or link compiling it into your application, 100 is the default, right? There's the same image at 70 quality at 45K. Now, I know we're sitting in a room and you've all been drinking heavily, hopefully, and you're on a projector and a digital ratio and all this other stuff, but you really can't notice significant details on this in an information-starved society where they bring up an image, look at it for 3 seconds, and then swipe away. Think about how many bits right now you are wasting sending to people that they look at for 3 seconds and swipe away. How much money you are paying for your content distribution network to send those bits down there, and how much they are paying to receive them. Now, I got to give props to Twitter. I did some analysis. Y'all are getting a little right. Twitter actually does do a good job of pre-compressing their images before they send them down, right? Especially the thumbnails. I found that most of y'all's thumbnails are actually compressed at around 60 quality level, 65, somewhere in there, right? Which is actually really good, because when I go to other social apps, it's not that good, right? Which actually brings us to something else. Reduce size, physical dimensions. You gotta remember, thumbnails take up less room on the screen, right? Less pixels, which means that there's less chances for the human eye to pick up those small little nuanced introductions for reduced quality. In fact, this is actually a quality 40 image that was output at 96 by whatever that one was, right? And it looks really good because it's that small on the screen. Now, of course, when the user clicks on that, you probably want to deliver to them a high-res one. But the fact is that you should not be sending down the high-res one at 4 megapixels to decompress it into main memory all the way to 32 bits per pixel to then resize it down to 96 by 128. If you're doing that, I don't want you to raise your hand. I just want you to drop your head in shame so I know who you are. I know a lot of you are doing it because I can see your code. Well, I can't see your code. I can see how your code works. But the truth is that a lot of people are doing this. They're actually sending around 4 megapixel images and going, oh, well, I'm going to need it in case they click on it, and I'll just resize it. I'll just render it at this resolution. That's a horrible idea. I've got a video up on Android performance patterns that talks about all the crazy stuff that Android has to go through to actually get that to a different size, including all the memory burdens, the garbage collector events that are thrown off because of that. You're basically screwing your entire memory heap because you're too lazy to pre-compress this stuff, pre-reduce the size of this stuff on your CDN side of stuff. And I say lazy because it's bad. Nobody? Okay, so. Everyone's like, he's right between that line where I should feel bad and I actually feel like he's yelling at me. I don't know. That's okay. Well, it'll get better. It'll get better. So the fact, though, is that if you're sending around 4 megabyte images, you should feel bad about this. And a lot of people are. I don't know if you're in the room. But the other thing is you should really be optimizing your image size based upon the device. Sending down a 4 megapixel image to a device that can't actually physically display that is just as bad. Right? Sending out a 4 megapixel image to a Wear device? Why? Right? Why would you do that? That's just idiotic, right? And then sending it down as a thumbnail. You need to have buckets. And so this is what I like to tell people. If you're serious about emerging markets, if you're serious about the next 5 billion Android users coming out of India, if you're serious about China connectivity problems, about South Africa and South America, you really need to move away from the mental model that an image is a static thing that your designers have domain over. No, this is all arithmetic. This is all numbers here. What I like to tell people is you really need, when an image comes to you, it needs to have multiple versions on your server, right? You need to have one for different resolutions, thumbnail size, quality levels, all of these things. Cloud storage is cheap, right? And if you send the optimized images to people, you're going to get it at a cheaper distribution cost. A lot of people like to complain with me on this, and they go, no, you don't understand. All the extra computation and the OR storage overhead, it's totally too much money for me to do that versus just sending the 4 megapixel image down. I go, no, it's not. It's not. You're paying to send 4 megs, and your user is losing money, too. You're pissing off your user, and I'm going to tell them. I said that to somebody at Google I/O, and they're like, oh, please don't. I don't know you. Anyhow, so I like to say that having a really good dynamic content serving machinery on your server side is one of the most influential things you can do to reduce data size. Number 2, serialized data. I'm going to say one thing here, and if you disagree with me, I don't care. If you can't tell that trend so far. JSON is horrible. Horrible. Horrible when it comes to compression. Horrible. Look at all this. JSON and XML are human-readable serialization formats. Think about it for a second. You're writing code, compiled into executable code, to create data to send on a network connection that some other human can read. Why? The human's not getting it and reading it. Another computer is getting it and reading it. Look at all this crap we have in here. Spaces, quotes, carriage returns, lines, colons, bracket. Why? None of this is needed. It's absolutely not needed. XML and JSON are some of the biggest offenders. They're in my opinion, they're sins against the humanity of the internet, right? This is horrible that we are sending around these huge blobs of JSON. And some of you in here, I'm not going to say who you are, but I know who you are because you're wearing your t-shirts, right? I know that you're sending these types of blobs to your server about 3 times every 10 seconds. Yeah, you should feel shame. I know you're in here. I've done analysis. So the fact is that this stuff is not needed. It is absolutely not needed. If you have a backend that's returning JSON and you're actually using that, holy cow. It doesn't even matter if it's gzip compressed. I know someone in here is going to walk up and go, actually, that JSON is gzip compressed by the HTTP stack. And what I'm going to tell you is, shut up, I'm getting to that. I told you it would happen. So basically, this is the reason. Hold on. Here we go. Getting to it. So the problem is this: is that remember that gzip is built upon two compressions algorithms, LZSS and arithmetic encoding. LZSS is basically a backwards multi-token matching window. Okay, which basically says I'm going to try to find the next 10 tokens in the past 32K bytes. Now, if I do not have a match in that 32K bytes, I have to just, no, you just literal token it out, right? So let's say that you've got structured data, right? Like you've got this is what we call an array of structs form, right? Where you've got like, let's go back. Sorry, now I'm all over the place. So you've got something like this, where you've got like ID and GUID and isActive and balanced and picture. When you page that into your compressor, the next ID value is more than 32K away. So it actually can't find another string to actually match. And this is why in the future, I was getting to this, I actually say like you need to adopt what we call a struct of arrays form, where you actually put all of your ID values in a contiguous set and all of your GUIDs in a contiguous set. That way when gzip comes through and it actually tries to do matching in its 32K window, it'll find more matches and actually compress your data better. So if you're absolutely caught on using JSON, at least do the right thing and transpose your data so you actually get real compression. Can I go back? Awesome. Yes. I did it. Mom can be proud of me now. Sorry. Damn it. Yes. I have more things to talk about, by the way. Okay.
I was using JSON because it's easy to log in and see the networking request.
Which is great for debugging.
Right.
You shouldn't ship that. Is a human reading that on the other end? Is it? Aha! Then why would you send it around? It's human readable, for God's sake. We're computers, we're building them. Use them. There are great solutions. Fear not, mortals. There are great solutions. Number one, proto-buffers. Anyone use proto-buffers? Proto-buffers are fantastic. They're a little bit tricky to use during debugging, yes, right? But they are actually a very good serialization format that produces binary files that are very small. Problem though, they suck on Android. The default serialization mechanism that actually is used on Android actually has a lot of memory churn overhead and extra API calls that basically just bloat your call stack. And it actually doesn't produce the best runtime environment in serialization and deserialization time. That's why we have nano proto-buffers inside the Android source code. If you actually go digging around the source code, we don't use proto-buffers. We use nano proto-buffers. And you can actually just take that file out of the source code and put it in your own app, and everything works the same way. And in fact, the nano proto-buffers are actually amazing because there is literally less memory allocations during serialization and deserialization and less API functions listed for the data set. So it's going to reduce your deck size. It's going to reduce the amount of memory that it uses in the overhead. It's basically what the Android team uses for their day-to-day stuff. And of course, my personal favorite is flat buffers. Now, for those of you who don't know, I actually come from the games industry where I was a GPU programmer. So the only thing I worried about every single day was how fast to render images to your screen while you're trying to kill those aliens. Like that's all I cared about. It was all about data and performance. You can kind of see how I got here and crazy, huh? Anyhow, flat buffers was actually built by one of our team members who focuses on building software for game developers. And because we are so anal retentive about performance in the games industry, much more than the application world right now, this thing is badass. And it works completely fine on Android. It's just as fast as proto-buffers and everything else. In fact, tangent really quick. By the way, this does not apply to the XML that your Android app uses for like layouts and stuff like that. All of that XML data that's being used in there is actually compiled into binary serialized data that's actually fast to load and actually put into your APK so that your load time is actually extremely quick. Funny how we did this for our stuff, but not for your stuff. Anyhow, back to flat buffers, okay? So flat buffers are fantastic. You can see this graph here. We're actually comparing binary flat buffers versus protocol buffers, rapid JSON, and XML. And this is encoded file size. So of course, you can see JSON is horrible, XML is horrible, and protocol buffers basically beats flat buffers in both of these scenarios, right? Now, here's the reason, though, why you're going to use flat buffers. This is the encode-decode times. Anybody spot the flat buffers time? Yeah. Now, a company in here who sends 3 JSON packets every 10 goddamn seconds? Imagine how much time it's taken to serialize that data. I know. Flat buffers is a fantastic serialization format that you absolutely should be using because, if only this reason, the encode time and decode time is just non-existent, right? Even though, as you can see here, it's probably not exactly on par with protocol buffers, like you get a little bit of overhead. So this is one of those great places where you get to make a trade-off, right? You get to say, like, hey, is this a time-critical serialization piece of data, or is this a size-critical piece of data? And I know you developers like options, so there's one free. Sorry. All the people in the back are still standing like, why the fuck are we standing for this guy? There's some seats up here. Nobody? Hi. Huh? Oh, yeah. Oh, there. Yeah, okay. I just saw like one finger come up and then put down. I was like, that's, you guys had more beer. Structive arrays. Do I need to do this a little bit more? Structive arrays, arrays of structs. We're covered? Next. Got it. So now let's talk about number data. Numerical data is the bane of my existence right now. It is by far some of the hardest stuff to compress. All of you in here who are sending around JSON data probably have some array index that has a list of numbers in it. You know, user IDs or inverted indexes to search query results that get passed back and forth between your servers, all sorts of numerical data. And the problem is numerical data from an entropy perspective is way harder to compress. Text data tends to be self-duplicating. The word "the" tends to occur multiple times. In the English language, the letter E is 44% the most probable letter of everything else, right? So if you have a block of text, you're going to have a lot of redundancy there. Number data, though, says, I don't even care about that, right? Most of the time, you have single instances of a number that's not duplicated anywhere else. Remember, statistical encoding works by taking advantage of the fact that there are duplicate symbols. So numeric data basically screws you over. Right? GUIDs, all that stuff. You're kind of boned. And this is where we like to use delta coding, right? Delta coding, super simple concept if you're not familiar with it. Basically, we take a run of numbers, right? And we subtract n from n minus 1, right? So the first number is 1, the second number is 3. So we subtract the first number from the second number, it gives us 2, right? So you see the middle row here is 3 minus 1, 6 minus 3, 8 minus 6, 10 minus 8, and you get the row at the bottom. Now, the reason that this is considered a contextual transform is, again, it's not actually compressing anything, but it's turning the data into something that actually takes less bits to represent, right? That original one up there took roughly about 4 bits per number to represent it, because the log 2 of the largest number there, 10, is 4, as we saw in the previous slides. However, the log 2 of the bottom set right there, if you subtract 1 from everything, so you get 0 to 2, is only 2 bits. So by applying delta encoding, we actually just compressed our set in half for like 5 numbers. No data redundancy there at all, just simple statistical movement, or simple mathematical movement, right? No stats. And decoding is actually extremely straightforward, right? We start from the minimum value and just add up as we go, and boom, we get our data right back. So very slow algorithm in terms of parallelization, unless you build in reset points along the way, but this is the basic concept. Now, delta coding for numeric data, though, can get you into a lot of trouble. First off, let's say you've got some low number of datas and then a huge one there in the middle. Well, when you apply delta compression to it, it really doesn't help, right? You still have this huge honking number that screws up the rest of your log2 information theory for the rest of your set. Or worse, you end up in situations where things are not linearly increasing, and when you do your subtraction point, you end up with negative values in your data set. So now you're really screwed, because not only do you have to represent your positive number line, but somehow represent your negative number line as well. And this is where delta compression, most people are like, well, fuck that, and just move on to something else, because like, what am I supposed to do with this? I'll just let gzip try to do something with it, I don't know, right? But the truth is that there are actually some cool solutions here. So first off, if you ignore subtraction and instead use XOR, you actually get a cool result, right? So let's take that same data set there. Subtraction leads to some negative numbers. XOR, however, right, just leads to some numbers in the same data range without negative values. So you still have to represent this larger number, but at least you don't have to have the mental concept of where in your code negative numbers are coming from, right? Everything is unsigned at this point. Another cool little thing here that I found a couple months ago is called frame of reference delta encoding. This one's really neat. Basically, the concept is you have some long stream of data here, and you've got some minimum value. And you choose that minimum value and then subtract that from every other value in the data set, giving you a data stream that's much lower, right? So because I've subtracted 107, which is the minimum value from everything, I now get a data set that doesn't need 8 bits per pixel, or per value. It actually only needs, what is that, 5 bits per value. So 30% savings there just from using frame of reference delta coding. That's pretty cool, right? That's a neat little trick to have in your handbag when gzip is failing on you. This is really meant for stream splitting. So if you've got a large number set, a lot of IDs, this frame of reference stuff is really meant to say, hey, let's actually break up streams of your data where these minimum values can be best applied. And so for that top stream there, you actually end up getting 2 streams. You know, 107 is the minimum value and 125 is the minimum value, ending up listing those in the front so you know what the minimum value is to apply to everything, and then delta encoding the rest of them. So boom. Again, here you end up with 107 and 125 are large values, but you can move those away and encode the rest of them in much, much less bits. Again, no statistical craziness here because we can't. We have to find other correlative ways to compress our data. Now, patched frame of reference is the natural extension of this, because what the hell do you do with those 107s and 125s, right? Like, that's kind of weird. Like, do we just, we're just given another data set, right? Like, it doesn't really help you there. So patched frame of reference will actually do something a little bit different. So let's say we've got 1, 2, 10, 256, okay? And when we do our delta encoding, we get 118 to 46, and so we don't really get any savings there. What patched frame of reference will do is it'll say, hey, let's take this exception. Let's mark an exception value, which is the one that's way too high, right? And actually leave some of its bits in the array and truncate the rest of the bits to another array, right? So here, 246 is actually in binary, 8 values of 1111 and 0101. If we leave the 0101 in the original array, we actually get 1185. And then we take the upper 4 set bits, and that actually equals 15, and we put that in another array. And now the entire thing can actually be compressed with 4 bits per value across the board. Nobody? Delta compression? Yay. gzip. Beer. All right. So compression is crazy. Let me get to you in a second. Compression is crazy. It's my personal addiction because I honestly believe that people don't learn enough about it. And given the fact that we're all mobile right now and how many applications are out there building stuff on the cloud and socializing individuals and finding new ways to connect humans, we're screwing up in a big time because we're not going back and obeying the fundamental the rules of data compression and networking when it comes to asset size. So there's a lot of stuff out there if you want to learn more. Number one, I've got a great series of videos out there where I explain all the basic algorithms of compression. It's called Compressor Head. If you search for it on YouTube, you'll find a good 6 to 8 videos where I talk about Huffman encoding, variable length codes, arithmetic compression, Markov chains, Burroughs-Wheeler transform, adaptive arithmetic compression transforms, and LZ77. Like, basically, I'm taking that data structures to a 1-style course, but I do it with Legos and silly putty instead of actual code. Kind of fun. Number 2 is there's a great article I wrote a couple years ago called Image Compression for Web Developers. If you've got someone on your team who doesn't understand anything I just talked about, just give them that article. It'll basically run them through the basics of how image compression works, lossy versus lossless, JPEG, WebP, PNG, how all that stuff comes together, and hopefully tell them to pull their heads out of their asses. With all due respect. Number 3, Krabby. I invented a GPU texture format for video games. So if you're a video game developer in here and you're looking to save residency size on GPUs, go check out the image format that I actually made. It won't actually decompress to CPU memory at all. It'll actually keep the compressed block format and actually sample it in the shader. So you actually get a huge redundancy in size there. Then there's also texture wrangling, which is a talk I gave at Game Developers Conference, which talks about how I did an analysis of 1,000 top games in Google Play and basically found that 73% of all textures used by those games were PNG files. And then I rant thusly. Then, of course, there's a great talk I gave. All my talks are great. You like how I say that? A couple years ago that talks about gzip and the fundamentals of gzip for the web stack, and how, as web developers and people sending data around, gzip is just not going to cut it for the next world of things. You need to think outside the box. I talk a lot more about PNG and why that's such a failed format there, too. A little bit more about JSON and XML. And, of course, text compression for web developers is another great thing that just helps people understand sort of the basics of archival compression. And, of course, flat buffers. If you're interested in the flat buffers format, I've got a video on that, too, where I talk about the internals, how it works, how you can go get started with that stuff. I do videos all the time, roughly about one a week now. Android performance patterns. You want to make your apps better? You want to keep your users happier? You want more money and an awesome house with a tiger and an elevator? Watch my show. It might help. And also make sure you join our Google Plus community. Here, stand up. Basically, every couple months or so, we do a community shirts here. Here, turn around. We do community shirts where we basically brand you with Android performance patterns swag, right? Give them the tour. Yeah, let them see here. Yeah, let's see both sides. Yeah. Round of applause here. Yeah. Who thought performance could be so sexy, right? So the G+ community is fantastic because there's a lot of us people in there who are just anal retentive about performance. If you've got a question, you want to see what other people are doing, just stop by there and check it out. If anything, it's just a resource to make sure that you're not doing anything too stupid, and then buy the shirts when we come out. Cool announcement. If you love performance, we are doing a performance-only conference at the Big Android Barbecue in DFW, Texas in October. Myself, Chet Haas, Rado Meyer, Timothy Jordan, we will all be there, right? There will be some surprises that we will talk about. We will unveil some new performance stuff that you've never seen before. It's going to be a huge, awesome party. There's going to be tons of Googlers there. Go get your tickets now. Register, book your flights. It's cheap. It's DFW. Who the hell goes to DFW? It's really fantastic. The Big Android Barbecue people were gracious enough to let us come in there and just trash the place this year. So make sure you come down there and watch what kind of train wreck it is. So with that, my name is Colt McAnlis. Thank you for your time. We'll open the floor to some questions. I think we have some time. Yes? All right, questions. I saw you had a question up over here, hair to the side guy. So very complex question. I'll try to repeat it for everybody else. How do you compress text data, since most of the talk was about image data and serialized data, and the context that he provided was if you're doing a bunch of server-side processing with gigs and gigs of text data, how do you properly compress that information? And then he mentioned SDHC, or shared dictionary header compression, or acronym, yeah. And why isn't more people encoding it? Let me start with that one first. Not a lot of people know about that because the performance of it is kind of contextual. Like, to get really good compression with the shared dictionary header model, you need to have a shared dictionary that's agreed upon between a server and multiple clients, right? And so you get the overhead of transferring around the shared dictionary and keeping that up to date. And then you get the overhead of, like, if something goes out of sync, you're basically screwed because you can't decode anything. And so it's actually a really gnarly setup to get done the right way. And then you leverage all of that implementation overhead against just gzipping it, and people go like, meh, it's good enough. I think I'm just gonna lay down and absorb some sun rays. Now, to get to your other part of it, which is like, how do you compress data for server sides that's doing processing and all this stuff? That's a great question, and Google has been trying to solve this in many different ways. If you actually pay attention to our blogs and what we talk about, we've shipped faster, better versions of gzip called Zoffly, Gipfeli, and Bertoli, which are all create the same gzip format, but produce the results faster and produce smaller results, right? At the cost of more memory overhead. And a lot of those things were built so that people can process large amounts of text data and encode it and decode it extremely efficiently and still have a resident in some data server somewhere. This could be like a huge conversation where I talk about all of the nuanced complexities with choosing an archival codec for a particular piece of data. I'm not sure we should get to that right now with other questions pending. Good. Next. Would I recommend all of the things I said today if your app also works on iOS? And the answer is yes. WebP works on iOS. Flat buffers works on iOS. Nanobuffers doesn't because it's a Java-only implementation. And protobuffers, I think there's a port of Objective-C. But basically, if you're looking at WebP, JPEG encoding, and flat buffers, absolutely, those things are all there. And even if you're running on iOS, you should still be cranking your quality settings down and resizing the damn images. and not using JSON. So I absolutely recommend all that. In the back, yes, sir. So two-part question. I'm gonna repeat it for you. The first one was SVG format, right? Where does that fit in the picture here? And number two is HTTP2 and speedy and the compression codecs that are involved there. So let me start with SVG. I didn't talk about SVG because mostly people have realized that the image, the designers have realized that the image quality that they can get from an SVG image isn't what they can get out of a JPEG image, right? And so typically they tend to author their stuff in Photoshop or upload it from a camera or a picture of food or whatever, right? And those things are called raster-based images that don't naturally convert to SVG format. Now, SVG is a fantastic format. If you're not familiar with it, basically rather than actually storing your image in a row and blocks of pixels, it basically uses a human-readable text format to describe the types of graphical transforms to apply to recreate that image, right? So basically when you load it into memory, and this is why a lot of people don't use it, when you load it into memory, you then have to go through and draw and draw and draw and draw and draw and draw and do each one of those little draw operations to recreate that image. Now, if you're doing something, the cool thing about SVG is you can, from one simple file, you can create a 16 pixel by 16 pixel icon or a 4 megapixel by 4 megapixel image. It's the same pipeline, right? You just spend more time processing pixels. And the modern SVG encodings or codecs should use the GPU to do that, which would be super fast, but I can't guarantee that across every version of Android or iOS, or the web for that matter. I know, I would like to say eventually, but who knows. The second one, HTTP2 and speedy, I gotta be honest with you, I'm not in with those teams as much as I should be. I've dabbled in speedy a little bit and kind of went like, I'm gonna get back to this a little bit later, so I can't really answer much on that right now. I apologize. More questions? Yes, sir. Oh, fantastic question. I gave a recommendation to optimize for size of screen ratio and whether or not it's a JPEG versus a large screen. Should you also be taking into account network connectivity? That's fantastic. That's really, so a lot of developers have the mental model that they like upload some static images and the CDN is basically just a directory style format and then they just grab, it's too complex to figure out what the matching algorithm is to figure out what the right image to grab down is. Once you move over to the mental model of like, oh crap, I gotta have like 30 different versions of these to optimize for my image transfer, you create something that's a little bit more scalable, right? Because when you get that first request for a 127 by 33 resolution image from a device in Uzbekistan that's never, because that's the phone they have there, and you don't have it on your server, right? You'll calculate it, cache it, and then send it back. And then when that phone blows up there and you get tons of those requests, now you've got it cached around. Once you build that infrastructure, you start getting more control over what types of assets you have, how you cache them, how you send them out. Now, one of the most important things here is how you're designing your application for high latency environments and communicating that back to your user. And so if you've actually designed it in the right way and said like, you know what, if you're on a high latency environment, I'm just gonna send you grayscale images, right? Or I'm gonna stop sending you images and just send you the color tone of the image, right? Once you start playing those games and you make that mental jump, like, oh wait, I don't have to send the image on every time. That's stupid, right? Like you can actually, your mind opens up and you're like, oh wait, I can do this, I can do this, I can do this, I can do this. And then you can start taking advantage of lower network environments and how you want to design your app around that. Specifically on Android, how would you check for network connectivity? I actually have a video about that. Coming up in a couple months. The basic idea is that if you actually grab Connection Manager and then do a call to get network subtype, it'll give you an enumeration, right? That enumeration can actually then be checked against Telephony Manager, Telephony Manager, and you'll be able to see if it's an edge network or an LTE network or stuff like that, which gives you the best uppercase value. But in reality, your network connection is gonna be really crappy compared to what that value should be for like LTE, because the server may be slow, or they may be far away from a cached data center or something on those lines. What I like to suggest you do instead is actually, as the user is using your application and there's a known data type size, so if you got a 128 pixel by 128 pixel image, and you roughly know that's about 1K in size, and they're on an LTE, it should roughly take about this many milliseconds to do. And so you start recording that over time, and when you start seeing that those requests get up and out of the range of what you would expect, and you notice the network changes or something happens, then you go, oh wait, something's wrong. Let's back out, let's design a different pattern and send some different images down, communicate to the server, add data to your request, stuff like that. Yeah, Android performance pattern video will come out down that pretty soon. Yes, sir. To repeat the question, there was a time when PNG didn't exist and it was just JPEG, and then we were said like, oh, you should totally use PNG because it's better, and if you set stuff up the right way with the right compression, you can get similar value, similar quality and similar compression. No, is the best way to put that. So remember that so PNG at its core is a lossless compressor, right? Now, if you apply a lossy preprocessor to it, right, then you're basically playing this weird game of like, I want to lossy preprocess something and then losslessly compress it. JPEG already does that, and it does a much better job of it too. You gotta remember the JPEG codecs have been around and being refined by very anal retentive photographers for over 30 years now, right? And that format and the JPEG-2 format and the JBIG format, like these are very hardcore compression gurus who are optimizing what's being removed. The PNG lossy stuff though is by hobbyists, right? Like Kodak has not come out and said, here is our PNG lossy preprocessor, right? And so sure, I'm sure there's a data set out there that given the right preprocessor and the right data set that the quality level and compression sizes could be equivalent between the two. But I don't think that that's anywhere close to being reality for 99th percentile of all the assets that you're gonna generate over the lifetime of your career before you get bald. Of course I'm bald, so preference goes to the guy in the Twitter jacket. Round of applause, by the way, for Twitter for having us here and letting us mess up the place. Thank you for letting us mess up the place. Everyone knock something over before you leave. Fantastic question. Has there been sort of large neural net research, learning machine research done on finding the optimal quality level for the human eye for JPEG images that come through? No. However, in the games industry, we had something very similar to this. Basically, what we would do is we would have our designers sit down and look at like classifications of texture. So there would be like, well, this is a UI texture, or this is an environment texture that's mostly dark, or this is an environment texture that only works in the desert world. And they would basically sit there and test some value ranges and say, for this bucket of classification, 70 is probably good, right? Or some value between 70 and 80 works, right? And then during the export process, when that artist would go export, right, we would say, oh, what bucket does this fall into? And then we would actually do a recursive quality checking process where we would export it at the upper value and then check the PSNR, and then the next step down, and the next step down, and the next step down, and the next step down. And we'd basically find the lowest value we could get before PSNR went under the threshold that the designer had set for that bucket of images. And so basically by giving your designers a little bit of freedom here and saying like, what, these are thumbnail images that are high resolution, or these images tend to be tagged with the word food or stuff like that, you can maybe get to something where you have this stair-stepping pattern to find the right PSNR threshold. But other than that, every image is so different that unless you have some human tweaking it right now, or you've got some crazy, other stuff that we don't know about, it's really tough to find the right PSNR metric, or SSIM if you're from Firefox and want to argue about that. Firefox, yeah. If that answered your question.
Sure, I'm wondering why nobody has done it.
Why no one has done it. Well, I mean, we've done it in the games industry for years. It's just kind of standard par for the course for a lot of the stuff we do. Not lately though, because everybody's been going to mobile and people forget about these basic things. But I mean, if you're getting an Xbox 360 game that's not using the Unity or Unreal engines, chances are someone has sat down and thought a lot about how these images should be compressed and how it fits on disk. Because remember, you got a DVD and everything's got to fit there. And so there's a lot of anal retentive attention of detail that's taken into these textures. And so that's basically the processes that we would build there. You had your hand up first. So a question about the support of hardware rasterization for Canvas, SVG, and CSS. As of like Chrome 32 or something like that, GPU is the dominant way that all CSS and HTML are rendered and rasterized. It's all done through the GPU paths. Canvas for Android has been GL compliant as of like Honeycomb, maybe a little earlier than Honeycomb. And so basically, unless you're running on like Android Wear, which is one of our only software rasterized devices out right now, you're pretty much guaranteed using the Canvas is going to be using the GPU. In fact, if you go check out any of Raman Gee or Chet Haas's talks, they talk a lot of deal about how they've actually moved the software rasterization process over to the GPU, and the Canvas is completely supported in that. Now, fun note though, there's a great Android performance pattern video called Performance of Custom Views, where we explicitly talk about the caveats of performance for those things. So for example, if you're using a canvas and you're tracing a path, we don't cache that. That's the most expensive thing you could do in the Android platform with respect to rendering. Like We can't cache that data. So every single frame, we have to recreate that path. And the worst thing is, we actually don't create a path of vertices. We actually create a texture that's the entire size of the canvas, and then punch out where your path is and apply that as a rendering process later. So we go over some of that. So check out the Android performance patterns video there. More questions? Yes, sir. I think the question you're asking is like, I figured out an automated way to go through and check out the texture format stuff for all of the APKs that I was able to grab. Is there a way for other people to do this, and how could I maybe use that to? Yeah, so how would we improve those applications that we found problems in? So for the game development side of it, the gist was that if you're using images that aren't being uploaded to the GPU, you should probably be using WebP instead of PNGs, right? Because again, WebP gives you the full matrix of features that you want, but it actually gives you better compression, better lossless quality, all these other things, right? And then if you are using GPU images, you should probably be using the Crunch texture compression codec. Crunch is a fantastic tool set built by Rich Geldrich, who I used to work with back on the Halo Wars video game. Basically, it starts with the GPU compressed texture and then applies a lossless preprocessor to it. So you get a smaller wire size format, and when it decompresses it, it goes right into the 1/4 resolution GPU format after that. And so finding the middle ground between those two is the right way. Yes, sir. So the question was, he's read that WebP is a better codec, but you're not finding built-in adoption in the photo editing tools. We have all of the plugins for all of the main tools on the page. So support is there. I won't get into the politics around softwares and supported formats and all the other craziness involved with it. Just if you walk into half of the Tech Valley companies here and just say the word WebP, like someone will like throw a chair at you for no reason and like JPEG for life. Why? What? Shut up. Why? Whatever. Anyhow, so sorry. More questions? Yes, sir. So if I understood your question, it was going one way and then you said something else that kind of confused me. You're asking about like, what if you're generating the image on the device and then sending it to the server, and then caveated with like, well, what if you're grabbing it on a computer and sending it to the server, and is the solution different between the two? Fantastic question. So if your phone can capture 19 megabit pixel images, even though it can't display it, what do you upload to the server so that other devices that could display 19 megapixels could actually take advantage of that? That's a fantastic question, and this is where we get into a lot of the caveats of this thing. In reality, what I would tell you is don't upload that file until the user is at home on Wi-Fi, right? Like that is bare minimum, because if you're trying to upload that on roaming charges, you're screwing everybody. Other than that, though, you have to find out as are we ever going to display this at 4 megapixels, right? And if the answer is no, then again, waiting for them to be on Wi-Fi and at home and then maybe doing some down resolution and then getting it up might be the better idea. Or again, if you've got a better cloud compute and they're on Wi-Fi, just upload the whole thing and let the cloud compute take care of it. But the general gist there is don't upload it now. Upload it later when conditions are much better, right? And it's fine to communicate to that to the user like, hey, you took this picture, I just haven't sank it to the cloud yet. If you know you're in a good place and are willing to take the bandwidth on that, please click this button. Like something along those lines of communication is probably the best route there. More questions? Yes, sir. So the question was, I thought Android optimized PNG for use. False. I actually talked about this in my texture wrangling talk. So I actually went and looked at the source code and talked to the engineers. The AAPT tool, like the Android Asset Packer tool, will only convert PNG images to a more optimized PNG format if they fall in like this specific type of bucket. Like if it's this type of texture without any transparency and it knows that it could get away with a 565 format, right? Or that it was flagged in some way. In reality, that's only some percentages of the PNGs that you're all doing. And that's only for, of course, when it's built, right? And so some subset of your icons are gonna fall in this bucket. Actually, none of your icons are gonna fall in this bucket because all of you are using transparency in your icons, right? So absolutely none of them are gonna get packed by the AAPT tool. Yeah, I talk a little bit more about that. If you want the larger, I've been hit in the head since then, so I forgot a lot about it, but I give the full discussion there. Yeah, I get hit in the head a lot, if you haven't figured that out. Yes, sir. So the question is, hey, WTF, Google's kind of encouraging PNG because it's kind of required by the Play Store and all this other stuff. Fantastic question. And in reality, any software doesn't have its shit together, right? Like point to one developer in this room who've actually got their shit together, right? None of us really do. Sorry, Twitter. Much love, Twitter. No, but the truth is, a lot of the stuff that we're doing with PNG for the Play Store is actually built towards what's the easiest way for you to get us data, and then we actually will convert it to WebP on our side. before sending it back down to the users. In fact, if you're actually running the Play Store in Chrome, you'll notice those are WebP images being loaded. And if you actually look at the network stream to your device, a lot of those are WebP images that you're sending around. And so we take in the PNG because we know it's going to be the highest resolution, as opposed to you screwing with compression on your own and making it bad, right? And then the store gets blamed for your bad image data. Our side kind of takes care of that for you. Now, I don't think that is a pass by any means, because we're definitely not doing that the right way for when you're actually compiling your Android application. So all your PNG files that you're putting in all of your resolution folders are definitely not going through that same pass. And I think that's kind of a cop-out. We need to fix that on our side, to be honest with you. Yeah. More questions? I saw some other hand back here that hasn't asked the question yet. Yeah. Got it. So the question is, like, when you're actually storing on disk the drawable formats like PNG, what is that actually doing? So this is a lot of working parts here. I'm going to try to make it as fast as possible. First off, understand that you're going to be bloating, of course, the data size, right? So the APK that comes down to the user is going to be much larger. On disk, your DEX size is going to be much larger, and your load times are going to be much larger, right? For those basic things, which is, again, unfortunate. I think we need to get our stuff together with respect to that and fix it a little bit better. Now, beyond that, I'm not sure if you're asking another specific question, like should we be doing X or Y? Got it. So you're asking about do the level flags you pass in to create bitmap in Android have so you're talking about like the pixel format from bitmap info. Yeah, yeah, totally, yeah, sorry. We're on the same page. Your hair is better than mine, that's why it took longer for me to catch up with you. So yes, absolutely. So in Android, bitmap info has a really cool little flag that's like, hey, what format do you want this in? So by default, just so you all know, even if you actually load a JPEG file, Android loads it at 8888. That fourth 8 is alpha. Right? So even though you're only using red, green, blue, we're putting an alpha channel in there when we load it into main memory. And that's because we need sort of a contiguous data set that we can manipulate for all the other APIs, and you don't have to worry about that as a developer. Of course, the problem with that then is it actually ends up on the GPU as 32 bits per pixel as well. However, if you can load your data and you know that it's only using 3 channels, you should actually set that 565 flag. And I've got a video on Android performance patterns where I actually talk about the right way to do this and the wrong way to do it. In fact, there's a really cool trick you can do where, because typically what will happen is you'll like load it off of disk and then you'll convert it to 565. Of course, so you're getting double memory copy there and all the extra overhead, but there's a way to do it right off of disk to 565. 4444 is another format that I recommended. Turns out I shouldn't have done that. Ramongi actually got pissed off at me because that's actually depreciated in the platform now. And A8 is a decent format if you're just looking to do grayscale. And the cool thing is with A8 and 565 is that those exist on the GPU as 16-bit and 8-bit per pixel images themselves. So you're actually getting better resonancy in CPU memory and better resonancy in GPU memory, which means when the device is now constrained by memory, your app is less likely to be the one that gets evicted. If I change everything to JPEG, will APT do it further? No. No. AAPT will only convert PNG files that fit the specific pattern of being able to not have transparency and potentially go from a 8888 format to a 565 format, and that's only some subset. So if you moved everything to JPEG, AAPT would completely ignore it. That's the only thing you get out of AAPT, which is kind of a bum deal, if you ask me. Yes, sir. To repeat the question is, networking libraries like OKHTTP and some others have like built-in support for JSON. It's actually really convenient because it handles serialization and a lot of other stuff for you. So serialization is a really misused process inside of Android. I got a video coming out on that too. I see a trend here. And in reality, the default JSON and XML serializables inside of Android are really bad. And so the ones in OKHTTP are a little bit better, but they're still using the serializable class as a type, and so that's actually a pretty big problem. What I do recommend is if you actually care about your users and you care about the data you're sending around, converting that stuff to, just grab the raw blob from OKHTTP and then using flat buffers, which by the way, will serialize it to a Java object for you. So you're still gonna get that serialization path to a Java object that then you can do query on. In fact, here's the really cool thing about flat buffers. You can actually query values from the flat buffer stream without deserializing it first, right? So you can actually leave it in its compressed format and get information out of it without having to serialize it to an object. That's really cool because you're saving you more memory. So, like one more question. I'm so sorry. It's like 8 o'clock. I got to give it to you because you've been waiting for longer and you asked me to speak here. So, Great question. Have we in Google ever talked about doing something smarter with APKs than sort of the brute force method? The answer is yes. And why haven't we done it is I can't talk about it. Sorry. There's a lot of people inside of that I work with and I talk with who are we're all on the same page of like, listen, we got to do something better here. Like we just have to do something better. And every time we come to like, what about this solution? Ah, fuck. What about this solution? Ah, fuck. What if we did this? Ah, fuck. Like and it's literally like when you have an ecosystem this big and you're trying to backport or innovate in this way, you end up with all these crazy caveats. It's like, ah, fuck. Well, legal won't let us do that. So and so won't let us do that. Well, that violates the term of service. Well, we can't do that in Germany. And like there's a lot of little weird nuances. In my perfect world, we would move away from an APK model to something that's like APK-like, where you have your core distributable code that's actually bundled and packaged with a little bit of overhead, and then we find some really good way to give you access to a CDN, right, that can handle image streaming and everything else, and like a front end that can do that stuff in the right way. Because I mean, for game developers, that's actually not going to work, right? Because the way the content works. But for the majority of application developers in our ecosystem, they send images and they send JSON blobs, right? And we can't control your server side that is doing the JSON blobs, but hell, we can compute images. we know how to do that. But that's in my own perfect world. Take that with a grain of salt. And when I propose that, I'm like, oh, well, we can't do that in Istanbul. So hey, I'm really sorry. If you all have more questions, you want to contact me. I'm sorry, I got to go. This is how to get a hold of me, plus Colt McAnlis on Google+, @DarRoach on Twitter. Thank you so much, everyone, tonight. I really appreciate it. Thank you.